Okay, good morning. So last time I sort of gave you a lightning introduction to how, or the strategy behind renormalization. And today we're going to talk a little bit more about how to apply this. So to apply renormalization in practice. So since we're physicists and physics is an experimental or empirical subject, we always have to go back to experiments. And so our first thing that we're going to do typically is to choose a process that you can measure experimentally. Okay, and if we're doing renormalization, one thing we learned is that the coupling constants and the masses and things that we're going to use depend on a renormalization scale, which we get to choose. So let's say you choose a appropriate mu, which is renormalization scale. So the choice should be roughly the characteristic mass scale or energy scale of the problem in question, which I called m bar. Right, so m bar is maybe square root of s for the process, or maybe it's the mass or some combination of those things, but it's something characteristic of the energy scale of the experiment. But it's sort of arbitrary. So now you can fit your data from your experiment to determine what G mu, and let's say, I'm just going to write down two parameters. There could be many more than two parameters, but let's say there's two of them, a coupling and a mass. And these are known as renormalized couplings and masses, or sometimes known as running. Okay, and then you get to predict results for other experiments. Okay, and then you repeat as needed. So one thing to be aware of in this process is that the original coupling and masses that we started with, which we call the bare ones, the bare quantities, which I put hats on, they never enter into this. You never actually have to talk about them at all directly, and they have no practical significance. So even though they're sort of the fundamental thing that's going on behind the scenes, they're not something we ever talk about. Okay, so here's a common problem that one runs into in doing this, is your best experiment might be an experiment that happens at one particular characteristic mass, but then other experiments happen at a different characteristic mass. So you extract your best values of the running couplings, or the renormalized couplings and masses, in an experiment with characteristic mass scale m bar equal to some particular mu scale, mu0. But you want to predict it. You want to make predictions for other values of mu. So for different experiments. Okay, at different mu's. And the question is how to do that. So another way of saying what we want is we need to know how our couplings depend on mu. Okay, so fortunately, this information is already built into whatever calculation you did to analyze the data. So this info built in or built into the calculation already. So this is another one of those things that seems kind of like magic, but let's figure out how it works. So the way it works is, let's go back to, for example, the example we did last time when we were doing quark-quark scattering. Let's say it wouldn't be, but let's just say that was the process that we were using to measure our couplings. So one thing we know about that is we know it's an observable. It's something that has an objective value. You can measure the cross-section for, I'm just going to write it as fermion, fermion prime goes to fermion, fermion prime. Could be quarks. It actually could be anything, could even be gluons. This is, so we know that this is an observable. It's something that can be objectively measured in principle. And so it can't depend on our choice of mu, because our choice of mu was arbitrary. So let's write down mathematically what that means. That means 0 equals the derivative with respect to mu of the cross-section that we calculated. Right? And so that was, if you work it out, or if you remember what we wrote down last time, it was the tree value times a correction. The correction involved 4 powers of the coupling, so it was something like this: 4 over g dg by d mu. What we're doing here is we're using the product rule. So it was proportional to 4 powers of the coupling, but then there was a correction part that looked like this. And there was some group theory factors. The Casimir of the adjoint minus 4/3 times the sum of the fermions times the index of the fermion representations. These are just group theory numbers. And that was all multiplied by a logarithm of mu plus some other stuff, but we don't care about the other stuff right now. We only care about the mu dependence, and the derivative of logarithm of mu is 1 over mu. Okay, and then you could add more bells and whistles by adding more loop diagrams, and that's the ... here. Okay, so because this thing can't possibly depend on mu, the only way is for all of this stuff to be 0. And therefore, we've learned what the derivative of the coupling with respect to mu is. In particular, mu times d by d mu, acting on the coupling, must be g cubed over 16 pi squared minus 11/3 Casimir of the adjoint plus 4/3 some other fermion representations, like so. So we've just figured out how the coupling depends on the renormalization scale. And so if we measure the coupling at one renormalization scale, we can use this equation to calculate what it is at any other renormalization scale. This right-hand side is famously called the beta function of the coupling. Okay, and the whole thing is known as the renormalization group. I'm going to write it as RG equation for the coupling. Okay, and the important thing about it is it's a first order differential equation. First order differential equations are great because you can always solve them. Even if you can't solve them analytically, you could use Runge-Kutta or some numerical method. First order differential equations are easy. Okay, so the idea is some experiment that you do, your best experiment, determines the value of the coupling at some particular renormalization scale. You use that as a boundary condition. And then you use this equation to find it at any other value of mu. So here I wrote down what you get at lowest order in perturbation theory that gives a non-zero answer, but this has been worked out in Yang-Mills theory, I think to 5-loop order, at least 4-loop order, and know for sure. So in Yang-Mills theory, which includes quantum chromodynamics as an example, the beta function for the coupling is of the form g cubed over 16 pi squared v0 plus g to the 5th over 16 pi squared squared v1, and then you just keep adding 2 more powers of g and another power of 1 over 16 pi squared for each loop that you've calculated, say, the cross-section for. Okay, and these numbers are known. So B0 is, we've just said, minus 11/3 the Casimir of the adjoint, plus 4/3 the sum over the fermion representation indexes. And B1 is, it turns out, now I'm just showing off by telling you that it's minus 34/3 CA squared plus 20/3 CA. Okay, so there's some group theory stuff that goes into this, plus 4 times the sum over the Casimir. I'm running out of space here, times the index. Okay, and then you can look up what B2 and B3 and B4 are. So that's if you're really interested in calculating the beta function to very high accuracy, which some people are. But let's think about what you would get when you actually solve these equations. And it turns out, for many purposes, you can, to get a qualitative idea, you only need to worry about this first term. And one of the reasons for that is you get an extra factor of 1 over 16 pi squared every time you add another loop. And so hopefully these get smaller and smaller. Not always, but hopefully. So at least qualitatively, to 1 loop order, I'm going to write d by d log mu. That's the same thing as mu d by d mu. And I'm going to write it for, not for g, but for g squared. This is just cosmetic, but it's going to turn out to be nice to write it this way. So this is b0 g to the 4th power over 8 pi squared. And the nice thing about writing it that way is that then you can solve this. I'm just going to write down the answer for you. The solution is g squared of mu is g squared of mu0, that's your initial condition or your boundary condition, divided by 1 minus b0 over 8 pi squared, g of mu0 squared, logarithm of mu over mu0. So this is a great way of writing it because you measure g of mu0, that's the result of your best experiment. You plug in that value, you plug in mu0, and then you plug in mu, and out comes the coupling at any other scale that you want. And then you can predict the results of experiments at that scale, at that value of mu. So the reason this is called a running coupling, of course, is because it depends on the mu that you choose. Okay, and you should choose mu to be whatever it is for the experiment that you're doing. What's the appropriate mass scale? So let's see how this works for QCD. This was the Gross-Wilczek Pulitzer Nobel Prize. for QCD, which has gauge group SU3 color, remember the Casimir of the adjoint for SU3 is 3. Actually, it's N for SUN. And the index of a quark or anti-quark representation is 1/2. And so if you plug those in, B0 for QCD is equal to -11. That's coming from here. Okay, plus 2/3 times the number of quarks. And you could say, well, we know there are 6 quarks. Why am I putting it as N sub Q? And the answer is because sometimes I'm interested in experiments at very low energy where effectively there are only 3 quarks. So NQ here is the number of active quarks in your theory. The number of active quarks is usually taken to be the number with mass less than or equal to the renormalization scale that you're interested in. Okay, so typically we work in an effective theory where the only quarks are the ones with only active quarks. So you just ignore the other quarks on the grounds that they're too heavy to affect anything. Okay, so if you plug in the number of quarks, possible things that would be interesting are 3, 4, 5, and we think the most there are is 6, if you include the top. Then the value of B0 for QCD is going to be -9, -25/3, -23/3, or -7. The key thing about these numbers is they're all negative. Okay, and so if we take this equation and we rewrite it in terms of the alpha S, which is G²/4π, then we get alpha S at some renormalization scale is alpha S over at μ0 divided by 1 minus, you plug in the appropriate B0 over 2π, alpha S of μ0 again, and then a logarithm. Okay, so let's look at this denominator a little bit. So we've got a minus sign here, but this is also minus. So together that makes a positive number. But the logarithm could be negative, because if mu gets much less than μ0, then you're taking a logarithm of a number less than 1. And so this can be negative. So the moral of the story is this whole denominator could go to 0 for small enough mu. Okay, so can blow up because the denominator is going to 0 for small enough mu. In fact, if you think about it, it sort of has to, because if you choose mu small enough, that denominator will eventually go to 0. So there's a nice way of rewriting the equation to see how that goes. So to see this, we can define what's called lambda QCD in the following way. It's 2π divided by B0, which is a negative number, times the logarithm. I'm sorry, I'm running this wrong. Lambda QCD is μ0. So you did some experiment at some value of μ0, and then it's the exponential of -2π over B0 alpha S μ0. So all of that's in the exponential, and it's all in the denominator. Okay, and then you get the equation that I was writing down prematurely. namely alpha S of mu, you can write as 2 pi over B0 logarithm lambda QCD over mu. Okay, so my claim is this equation just follows from taking this definition and plugging it in here to this equation. Right, and so one way of saying what you're doing is you're eliminating alpha S of mu 0 in the right-hand side. So you can solve this for alpha S of mu 0, plug it in, and then do a little bit of algebra, and you end up with this equation here. So this is great because now on the right-hand side, there's nothing that depends on alpha S at all. There's just this lambda QCD scale, some fixed scale. Everything here is a constant. And so we can graph what this looks like. Actually, let me do it here. So this is as a function of the renormalization scale. There's some particular scale, lambda QCD. And when mu equals lambda QCD, this logarithm is the logarithm of 1, which makes it 0, which means we're going to infinity. So the graph of this is going to look like something like that. Okay, this is the asymptotic value. Okay, and along the way, the definition of the beta function changes, or the B0 changes. So for example, there's somewhere up here is M top, and then there's M bottom and M strange. And I haven't drawn it very well, but the slope of this line is changing or is different in these different regions because basically the B0 is changing. Okay, so what we've learned is that the running coupling is actually blowing up at low mu, or you should think of that as blowing up at low characteristic energy of your experiment. Another way of saying it is for alpha S of mu too big, then our coupling is too big and perturbation theory is breaking down, or has to break down. Perturbation theory is all based on the idea that the coupling is not too large. Okay, and that happens for a value of mu close to lambda QCD. So that means our calculations are in big trouble when mu is too small, but when mu is nice and large up here, then I should say what I'm graphing here. This is alpha S of mu. Okay, if I'm up here, then perturbation theory is actually okay because the alpha that we're using is not too big. It's down here at low energies, low characteristic energies that everything goes wrong. Okay, so another way of saying that is for large mu, okay, that's the characteristic energy of the experiment, perturbation theory gets better. And the code words that go with this are, this is asymptotic freedom. At asymptotically high energies, I can't spell asymptotically. Asymptotical freedom. Okay, and then for small mu, namely mu near this scale lambda QCD, that's called infrared slavery. And so one way of explaining why all the quarks and gluons are bound within protons is that at that characteristic energy, the coupling is so large that they can't escape. In fact, the closer you get to this, the coupling actually goes all the way to infinity. And so that's why nothing can escape beyond a mass scale below this, which is a distance scale larger than 1/. Okay, so the upshot of this is quarks, gluons only appear as bound states. Okay, questions on that before we contrast with what happens in QED? No questions?
I guess, so is this also telling you that if you could probe a high enough energy scale that, you might see a bare quark?
In some sense, yeah, but the problem is if you're, so when we treat the top quark, we're really treating it as if it were a free particle for this very reason. So top quarks don't form bound states, they decay too quickly.
Right.
And that's another way of saying the energy scale associated with them is so high that we can treat them as free particles.
Okay. Yeah.
But for everything else, for bottom and strange, for their bound states.
Got it.
Okay. So another way of discussing all of this is the code word is dimensional transmutation. Because you can think of what we just did as trading the coupling alpha S or G3 or whatever your coupling is in your theory. This is a dimensionless coupling. But what we've done is we've traded it for knowledge of lambda QCD, this energy scale, which has dimensions of mass. They contain the same information. Okay, and so if you measure, and here's a typical measurement of alpha S evaluated at a nice high scale like the Z mass, that just turns out to be a good place to measure it. So the nice thing about choosing a nice high scale is perturbation theory is not too bad up there. Okay, and so that's usually why we choose that scale. And we say it's 0.118 approximately, plus or minus 0.002 or something like that. And this is in the 5 quark theory. So this is in the theory where you're neglecting the top quark. Then you can translate that into lambda QCD numerically is about 210 MeV. But if you do the 4 quark theory, then you have to redo everything. So the 4 quark theory is where you don't have bottom, you only have up, down, strange, charm. Then the lambda QCD in the 4 quark theory is quite different. It's about 300 MeV. And I don't know why I wrote GeV here. This is MeV. Okay, so qualitatively, this picture is right, that there's some scale lambda QCD where the coupling blows up. If you know where it blows up, that's the same thing as knowing this whole trajectory of the coupling as a function of mu. But the actual value where it blows up depends very strongly on your effective theory of how many quarks you're treating as active. Okay, but so people will quote either alpha S and MZ, or they will quote lambda QCD, and usually they quote lambda QCD if they're interested in low energy stuff, and they'll quote alpha S MZ if they're interested in high energy stuff, like, for example, top quark physics. All right, so let's compare now to what happens in QED. So compare to QED. Oh, I should mention one other thing about this. The fact that this shape is what it is crucially due to the fact that the beta function is negative. And before Gross and Wilczek and Politzer, it wasn't actually known that it was negative. In fact, a lot of people doubted that you could even have a negative beta function in a quantum field theory. But it's the fact that it's negative that leads to this infrared slavery and confinement. All right, so let's compare what happens in QED. We're actually going to find a positive beta function. And the main reason for that is the Casimir of the adjoint for a U1 group is 0, which means that term in the beta function that was negative is just not even there. So in fact, B0 for quantum electrodynamics is a sum of positive numbers. And the positive numbers are 3, which is the number of colors, times the number of up-type quarks that have charge 2/3 times 2/3 squared, plus 3, that's the number of colors times the number of down-type quarks, times minus 1/3 squared, plus the number of charged leptons times their charge, which is minus 1 squared. Okay, and this is just working out the algebra, 16/9 NU plus 4/9 ND plus 4/3 NL, where NU equals the number of up-type quarks, meaning up, charm, or top, right? So it's either going to be 1, 2, or 3. ND is the number of down type, meaning down, strange, or bottom. And NL is the number of charged leptons. Neutrinos don't count because they don't have charge, so they just don't even talk to QED. Okay, so if you're doing an experiment with, for example, characteristic energy between the mass of the electron and the mass of the muon, then the only thing active is the electron. So only the electron contributes. Okay, and so B0 for electromagnetism is 4/3. And the renormalization group equation looks like this. This is the beta function for the electric charge. It's E cubed over 16 pi squared times 4/3, which is small, very small, and positive. For lower energies, lower than the electron mass, then there's no active charged particles. Okay, so the beta function, or equivalently dE by d log mu, is just 0. And that means E, or alpha, the fine structure constant, goes to a constant. That's why it's called the fine structure constant at low energies. Okay, so if we graph what this is going to look like as a function of mu, this is going to be the fine structure constant for QED. And let's say I put, this is not going to be to scale. So I'm going to put the electron mass here, and I'm going to put the muon mass, and up here maybe is the top quark mass, right? So this is going to start at a constant value of 1 over 137. And it's not going to run at all until it gets to the electron mass. And then it's going to start getting larger because the beta function is positive. But it's going to get larger very slowly. So it does something like that. But eventually, just like the QCD coupling blew up, this is eventually going to blow up at very large energies. But here's the key thing. Those energies are incredibly high. So this is the Planck mass. I'm not drawing this to scale. And the energy scale at which this QED coupling blows up is called the Landau pole in the renormalization scale. And the mu for that is approximately 10 to the 275 GeV. So first of all, we're never going to run into that experimentally. And secondly, we have no reason to believe that that's even what we should be doing. Presumably, once we get up to the Planck mass here, we shouldn't even be doing this theory anyway. We should be doing some different theory probably. Okay, so there's this Landau pole, but it's of zero practical significance for QED. And so basically what's going on is it's this fine structure constant is running, but very slowly, and that's why we can often treat it as just approximated by 1/137. Okay, any questions on that? All right, so let's go back to QCD for a little bit. And we're going to talk next about another process. We talked about quark-quark scattering, and now let's talk about gluon-gluon scattering. And this is mostly just to give you an idea of how it goes for gluon-gluon scattering. So this is, at first glance, this is going to be similar to photon-photon scattering, which I gave you for homework to draw some diagram for that in QCD, but it's actually not like that at all. So recall, okay, so the process here is going to be gluon-gluon goes to gluon-gluon. And recall, in quantum electrodynamics, you could have that process with photons, but this only occurs at one loop level. There are no tree level diagrams at all for photon-photon goes to photon-photon. Okay, and that's just because photons don't interact with themselves. But in QCD, this occurs at tree level. And as proof, let me just draw you some diagrams. Okay, and by the way, this is relevant for example, proton-proton scattering, like at the LHC. So at LHC, and then the old-fashioned proton-antiproton at the Fermilab Tevatron, now unfortunately turned off. Okay, and so the Feynman diagrams that you can draw, it turns out there are 4 of them. And here they are. Okay, so there's one. Remember, there is a gluon-gluon-gluon vertex in the QCD theory. And so I can draw this, whereas there is no photon-photon-photon vertex. So I can't draw this for photons. And again, for gluons, we tend to draw the lines as squiggly or springy lines. So that's one diagram, but here's another one, where this is a T-channel exchange of another gluon. And then I can have a U-channel exchange of a gluon. And there's one more diagram, because there is actually also a 4-gluon vertex. And so those are the 4 diagrams. So if we were to calculate this, it would take us quite a while. And so I'm not going to calculate it. What I'm going to do is write down the matrix element for one of the examples, namely the first one. We're going to write down the reduced matrix element for this. And then I'm not even going to calculate that. I'm just going to jump to the final answer that you get from all 4 diagrams put together, because it's a nightmare of algebra. Actually, it's a nightmare of algebra unless you're a computer, and then it's all very algorithmic. And so people have written programs like MadGraph is one that I've used a lot that just do all this stuff for you. All right, but let's just struggle through one time to see what it will look like. So let me draw the diagram a lot bigger because I'm going to need to label some stuff. So there's one gluon. Here's another gluon. Here's my S-channel virtual gluon. And then my two final state gluons. And each gluon carries a vector index, so mu, and a adjoint representation index, A. So for that gluon, I'm going to call it mu A. For this one, I'm going to call it nu and B. For this one, it's going to be rho and C. And for this one, it's sigma and D. Okay, one vector index, one adjoint representation index. And then this virtual gluon in the middle, I need to do the same thing. So there's going to be a kappa and an E and a lambda and an F. All right, and then I need to keep track of all their momenta. So let's call this momentum coming in P, and this momentum coming in P prime, and this momentum coming out F, K, and this momentum coming out is going to be K prime. And then momentum conservation tells me the momentum, and this one is P plus P prime, or equivalently K plus K prime. Okay, and I think we've now labeled, let's call the polarization vector epsilon1 here, epsilon2, epsilon3, and epsilon4. And those things carry the vector index mu, nu, rho, and sigma, respectively. Okay, so now I've thoroughly labeled my diagram. And so now I can write down the matrix element for GG goes to GG only for the S-channel diagram. Let me start by writing the external polarizations. There are no fermion lines in this diagram at all, so I don't need to worry about them. And these ones are in the final state, so I should complex conjugate them if it makes a difference. Okay, and then I need to write down the factor for this vertex. So if you go back and look at the Feynman rules, that factor was minus G. There's a structure constant factor. And then there's a bunch of metrics and momenta. And it gets, you have to stare at these things for a while to get all the factors right. But I'm just writing them down for you so you can see roughly how it goes. Okay, so that's for this vertex. For example, the group theory parts are A, B, and E, and that goes into the F, A, B, A, E, B. The Lorentz indices are mu, nu, and kappa, and so notice each term has mu and kappa and nu in it. Okay, and then you have to take into account the fact that the momenta occur in this vertex too, and those are the factors that you get. Okay, and then there's a similar factor for the other one, and that's minus G F CDF, and similarly G rho sigma, K prime minus K, 2 plus G sigma lambda. Okay, so you can see this gets to be a lot of terms because you're going to have to multiply all these terms times all the other terms. And then finally, there's the propagator for this internal line, which if we do it in Feynman gauge at least is not so bad. And this denominator is just going to be S, Mandelstam S. All right, so that's it. That's it for the one diagram. Then you need to do the other three diagrams and add them together. So right other three diagrams. Add them together. And then you need to square it for the whole thing together. And then you need to sum over final state and average over initial state. And you need to do that for both colors and polarizations. So polarizations that are hidden in the epsilons and colors. Okay, and so that is going to be 1/2 sum over lambda 1 polarization, 1/2 sum over lambda 2 polarization, sum over lambda 3, sum over lambda 4, and then 1/8. When you're averaging over colors, there are 8 colors for gluons, so you have to do 1/8 times the sum over their colors, 1/8 sum over the glue of the other gluon colors, and then sum over the final state ones. So you got to do all those sums. There's quite a bit of group theory involved with the Fs. Okay, but that turns out to be the Casimir of the adjoint operation. And so let's skip. I just want to show you what the final answer looks like. The most interesting thing about the final answer is that it's so incredibly simple, considering how complicated all the steps are to get it. So you can write it down on one line pretty quickly. It's 9 pi alpha s squared over 4s squared. So let me just pause for a second to say where that comes from. So the alpha s is, notice there's a g and there's another g. So there are 2 g's in each matrix element, but then you square it, which means 4 g's. 4 g's can be traded up to factors of pi for 2 alpha s's. So that's where that comes from. The 1 over s squared comes from the definition, and then because we're computing d by dt, which you can trade for d by d cos theta. Okay, and then the rest of the expression looks like this: u squared plus t squared over s squared plus s squared plus u squared over t squared plus s squared plus t squared over u squared plus 3. Okay, and if you want, you can think about these as coming from respectively the different, this is from sort of the S channel diagram squared, T channel, U channel, and then this is the 4 vertex, although it's not quite that simple. One reason it's not that simple is because, remember, you can always trade one of U, T, and S for the other one. Because remember, S plus T plus U for massless particles is 0. So anyway, it's kind of remarkable. You have this horrible expression. This is just part of it. You got 3 more things that are equally complicated. You add them all together, do a bunch of algebra, and the answer is so simple that you can just write it down on one line like this. It's kind of amazing. Okay, now what are we going to use this for? It turns out we're going to have to combine this with the formula that we did for quark-quark scattering. And so we'll go into more detail about how that works next time. But if we scatter, so suppose that we're going to do proton goes to hadrons at square root of s is 13 TeV, for example, at the Large Hadron Collider. So the protons are made out of quarks and gluons. So I'll write gluons and quarks. It's actually the gluons that are often more important. And antiquarks. And the hadrons in the final state are also. So what we're really going to have to do is we're going to have to get an answer for something we can actually measure, we're going to have to take this expression, and we're going to have to take the expression for quark-quark scattering that we had before, and we're going to have to combine them in some way. So we're going to combine the scattering of the individual partons. Partons is Richard Feynman's word for quarks, gluons, and antiquarks. Okay, so we will learn how to do that on Friday. Any questions? All right, if not, then I will see you all on Friday.
Thank you.
Okay, have a good day.